All right, this is the video for section 4.3. In 4.3, we're just going to be taking the derivative of the natural log function. All right, so let's look at the derivative of the natural log function. So here I've graphed the natural log function. So remember, it starts out, it's only defined for positive numbers. And for small positive numbers close to 0, it's really, really negative. For large positive numbers going out to infinity, it blows up to positive infinity. So if we're talking about the derivative, remember that can be represented by the slope of the tangent line at a point. So let's look at some point that's over here where x is a very small positive number. For that, we'd have a tangent line that'd be very steep, right? It'd have a positive slope and be very steep. Right? If we move to the right, somewhere over here, if we look at a tangent line there, be over here. That would also have a positive slope, but maybe not as steep as it used to be when it was over here. And if we kept going, for really large x values, we'd still have a positive slope, but notice it's going to start tapering off and it'd be really flat out there. So we need something that the derivative, we know it has to be really large for small numbers and really small for large numbers. And what does the trick is 1 over x. Right? So if f of x is natural log of x, the derivative is 1 over x. So for this section, we're going to be just taking derivatives where we would be using product rules, chain rules, maybe quotient rules, regular old derivatives like we're used to, but we're going to... Okay, so now we've got f of x is natural log of 4x, and we're asked to find the derivative. All right, so one thing to notice is natural log of 4x is not the same as natural log of x. And in fact, what we have here is a chain rule where the outside piece, I've underlined with that big thing, that's natural log. And the inside piece, I've also underlined, that's the 4x. So if we want the derivative, we have to remember the chain rule. We take the derivative of the outside, so we need the derivative of natural log. And so that's 1 over, and then not x, but we want to copy down everything on the inside. Right? So that's the derivative of the outside where we plugged in the inside 4x. And then we multiply by the chain rule, so we multiply by the derivative of 4x, which is 4. So it's 1 over 4x times 4. If you leave it as that, that's perfectly fine. But one thing to notice is that those 4's do cancel, and it's still 1 over x. So because of this chain rule, anytime you have just some number times x on the inside, you'll always be able to cancel that number, and the derivative will still be 1 over x. You have to show me this chain rule thing. Right? So don't just write down 1 over x, or I don't know if you know what you're doing, or if you only remember 1 over x because you saw a log. Right? So again, anytime it's just a number times x on the inside of the natural log, it will cancel, and the answer is still 1 over x, but you have to show me that act of canceling over here. Okay, so there we used the fact that we knew the derivative of the natural log, but we also used this example. F of x is natural log of x squared plus 3. So again, we've got a natural log, so we know we're going to need the derivative of that. But we have something on the inside that's not just x all by itself, so we're going to use a chain rule again. So what does that look like? Well, we want the derivative. So for the chain rule, we do the derivative of the outside. So for natural log, that's 1 over everything, right? So that's 1 over x if it's just an x in there. But if it's not just an x in there, then you do 1 over all the stuff on the inside. So that's our derivative of the outside where we left the inside all alone. And then we have to multiply by the derivative of the inside, and the derivative of x squared plus 3 is 2x. Again, don't simplify this, and there's your derivative. We used chain rule again, using the fact that we knew the derivative of... Okay, what about this guy? So we've got natural log of, right, and then these big parentheses, which I'll put in red, and all the stuff inside there, that 4x squared plus 10x to the 7, that is all inside that natural log. Again, we just want to find the derivative. So looking at that, you should think, okay, that looks like it's going to be chain rule again. So we could do this one of two ways. We could do a chain rule, and then whenever we have to take the derivative of this inside piece, you should hopefully notice that'd be a chain rule as well. Or we can use properties of natural logs, and we can pull this 7 out to the front, and then we don't have to do a chain rule when we get to that derivative. So I'm going to do that this way first, and then I'll do it the other way. So what we want to do first is rewrite f of x as, and we're going to pull that 7 down, 7 times the natural log of 4x squared plus 10x. All right, so if you remember that property of natural logs, that makes the derivative a little bit easier. So let's take that derivative. What do we do when we have a coefficient sitting out in front? Anytime we're taking a derivative, we just are going to bring it along for the ride. So that 7 just comes along for the ride, and we want to multiply by the derivative of the natural log piece. And that, again, is a chain rule. So for the chain rule with natural log, you do 1 over all of the stuff on the inside. That all goes in the denominator. So 4x squared plus 10x. And then using the chain rule, we multiply by the derivative of the inside, which is 8x plus 10. And that's our derivative. You don't need to simplify it or do anything else. You can leave it just like that. Well, what if, I'm going to draw a line here separating this. What if you didn't remember this property that we used where we pulled the exponent out into the front? What would that look like? Because that's still a perfectly acceptable answer, and it's still correct. Doesn't matter which way you do this. So how do we do that? Well, we're going to do the chain rule just like before, but this time the denominator is not just 4x squared plus 10x, but it's that raised to the 7. So we get 1 over 4x squared plus 10x to the 7. So again, the derivative of natural log of x is 1 over x. So for the chain rule, you do 1 over everything on the inside. And then we're going to multiply by the derivative of that inside. So we're looking for the derivative of 4x squared plus 10x to the 7. And now we have to use another chain rule. So the 7 comes down. We copy the inside alone. Hopefully this is something you're comfortable with from chapter 3. And the 7's now going to become a 6. Sorry, this was in chapter 2, huh? Even further back. And then the chain rule says we multiply now by that derivative of the inside, which is 8x plus 10. And that would be the derivative. That's the way it would look if you did not use this property of natural log. Of course, these two things are equal. It does not matter which way you do this. It is the same answer. You could just cancel this 6 here with that 7 there, and you'll get the exact same thing. I don't care already. Now we've got the derivative of f of x equals 4x squared times natural log of 3x minus 1. So for this, we're going to have to use a product rule. So remember the product rule, we always have to have a first guy and a second guy. Our first guy is this 4x squared, and our second guy is the natural log of 3x minus 1. All right, so let's remind ourselves the product rule. You take the derivative by taking the derivative of the first, multiplying it by the second guy, and then adding the derivative of the second guy, multiplying that by the first guy. So what's the derivative of the first? So first, I'll label that, and second. The derivative of the first, well, that's 4x squared. Its derivative is 8x. So that's the derivative of the first. And then we're going to copy down the second, leave it alone. So that's the natural log of 3x minus 1. Make sure you put these parentheses here. That tells me that all of the 3x minus 1 is inside of that natural log. So that's the first times, I'm sorry, the derivative of the first times the second. And now we need to add the derivative of the second times the first. So the derivative of the second, remember the derivative of the natural log is 1 over x. So we do 1 over and then copy down everything on the inside because we're going to do a chain rule here. And then what's the derivative of the inside? We get a 3. So 1 over 3x minus 1 times 3, that's the derivative of the second piece. And then we're just going to multiply and not change that first guy. So that's the first times the derivative of the second plus, I'm sorry, the derivative of the first times the second plus the derivative of the second times the first. And that's our answer. No need to simplify. Okay, so now it says the cost to produce X thousand pounds of cat food is given by this cost function. If the manufacturer is currently producing 50,000 pounds of cat food per day, how much can the cost be expected to change if production is increased to 51,000 pounds per day? All right, so hopefully you already can see how we're supposed to do this one. So we've been given a cost function. It says they're currently doing 50,000 pounds, and we want to estimate the change when we go up to 51. So you should immediately be thinking that's marginal change, right? Marginal change, because we're increasing our x value by 1, and we want to estimate the change in our function. So in order to do that, we need to first take the derivative, and then remember we'll plug in the lower guy. So what we want to do is take the derivative and plug in x equals 50. So what is the derivative? Well, here's where it might be helpful again to rewrite our original cost function. So I actually don't want to do the derivative just yet, just regular old c of x. And I can rewrite it again by using my properties of natural logs. So I'm going to highlight here, I've got the square root of all that stuff, and that's inside the natural log. Right, so I can rewrite that. Instead of a square root, I could write it as, oops. Sorry about that, don't know why that happened. I can rewrite that as 100 times the natural log of, and then I've got 4x squared minus 300. And then instead of a square root, I'm going to write that as to the 1/2 power. And now by my properties of logarithms, I can take that power and go multiply it out in the front. So what's 100 times 1/2? Well, that's just 50. So I can rewrite this function as 50 times the natural log of, and now my 4x squared minus 300 does not have an exponent on it. Okay, so all I've done, I haven't taken a derivative. All I've done is rewrite my cost function using properties of the natural log. If you don't remember this property of the natural log, you can just take the derivative and you'll have an extra chain rule involved, but it won't change your answer at all. We'll do it from here though, assuming we did remember this property of the natural log. Remember we were doing marginal change, so we need to look for the derivative. So what's the derivative? All right, so we bring down our coefficient 50, comes along for the ride. The derivative of natural log of a bunch of stuff, you do 1 over all the stuff. And then chain rule says we want to multiply by the derivative of that stuff. So we're going to multiply by 8x. And so there you go. It's 50 times 1 over 4x squared minus 300 times 8x. And what we want to do here is plug in x equals 50. So what we're looking for is c prime of 50. And that's going to give us this estimated change in our cost function. So check my work here, but what I got is $200 over 97. So again, I plugged in 50 and I got 200 over 97, which is about 2-ish, right? It looks like almost 200 over 100. It's about 2.06. So it says, all right, and that's it for 4.3. All we really learned that was new was that the derivative of natural log of x is 1 over x. If you can remember that, and if you are comfortable applying it to all of the Chapter 2 derivatives using product rule, chain rule, quotient rule, and using it with marginal change, then you're good to go. Oh, there's baby Sully. That was before I even got him. Wow, he was probably like 2 or 3 weeks old in that picture. I'm sure you guys will enjoy that. I do. Anyway, there's your problems from 4.3. Go ahead and look at those and make sure you come to class any questions that you have over this section or using any of these product rules, chain rules stuff, marginal change with natural log. And that's it.